Okay. Phew. Well, that's complicated.
We don't have a big enough space.
Okay, all right, so, couple things, put your name in the chat window. Thank you. And, I don't really care if you hold the questions, you can interrupt me, but if it was a live session, that would be useful.
April 22nd.
If you have a question, you can throw it in the chat. Maybe I'll catch it before you can interrupt me. And remind me to start recording if you think I didn't record, because I have a good habit of forgetting to do that. Okay. The last thing is on my schedule, original schedule, April 22nd was the planned special test date for everybody that's taking exams, taking courses. Bob's group and my group will both test on the 22nd. I was going to try to move it a week, but because they don't want to do it. So we're going to leave it on the 22nd. Unfortunately, if we have the last session on a Friday night, that would be the testing would be Saturday morning, the day after we finish the last one.
I won't be doing that.
Which I think is clumsy for you. So here's what I suggest. I will have to skip the 1 week because I'm going to be in Connecticut doing a presentation. And I don't think I can do it that night. However, instead of having the class on Friday night, I'd be happy to have the class some other time between then and the following Friday so that you could have a few days before you have to take the exam. So I don't know what a good day is. I'm open to Sunday night. I'm open to Monday to, another night. Since you guys are on, do you have a preference? Or do you want to think about it? Because we got a few weeks to think about that.
I'm ready any night.
Okay, Harry, any bad night? Are there any bad nights to avoid? Thursday's probably not a good night for me, so.
Monday night's the only bad night. I have a lot of meetings on Monday nights, but that's it.
Okay, Tuesday is actually a pretty good night for me too. And Sunday night's available too, but let's plan on Tuesday for now. We'll keep saying that unless somebody really wants to. That way you've got a few days. You can call me up, ask me questions, whatever, between that day and the exam. If you're not local, that's not going to matter because, you'll have to take the exam wherever you want in your local area. And there's plenty of opportunities to take exams in a lot of places. You don't have to take it with our group either. You can take it later in June or whatever. The reason we used to push to get the exam done is that all of you that pass will be upgrades, and upgraded exam, and anybody that gets an upgrade can operate in our Get on the Air tent at field day at the end of June. So we love having people who upgrade or get new exams come down and get some experience at the Get on the Air tent that we run. And in the past I did that. Hopefully I don't have to do it this year, but we will definitely have a big, strong presence at the Get on the Air tent. And you can make some contacts and gain some points for the club. Okay. All right. So that's some formalities here. All right. I'm gonna move to this slide. Why didn't that move? Hello. There we go. All right. This should look familiar.
Okay.
Okay, and the red arrows are what you probably did, because I think everybody on tried this and got it right. So what you did is you took a vector and you went in this direction, and then you did addition of vectors. You took another vector, you started from where you left off, and you went in another direction at another distance. And when you got here, up here near Fall River, you ended up adding, or you made addition of 2 vectors. That's what you did. And then
11.
when you did that, you actually added two things together, which in electrical terms, these vectors are called impedances instead of resistances. So an impedance is like a resistance, except that it's a vector instead of a number. So in a circuit diagram, it looks like this. This is an inductor, this is a resistor, this is a capacitor. We're going to talk about this a little bit more. And this is a resistor. These are all in series, as it's called, and you add up each of their individual impedances to get the total of this whole thing. Well, that's what you did when you took this vector and this vector, because this vector is actually 60 ohms plus 45 at 45 degrees, and this one is 50 ohms at minus 45 degrees. And you just did a complex circuit analysis by doing these two vectors. So that's why I'm having you draw maps. I'm not trying to get you to go to forever. Okay, the other thing that you did is you took a circle 53 degrees from where you started, because this is the middle of what's called a coordinate system, or this is the middle of your map. I like to call the middle of the map. I like to, I have another analogy that I like to use, which is the Wizard of Oz. And in the Wizard of Oz, the middle of the map is the Emerald City. And that will have some interesting implications with yellow brick roads and stuff later. But anyway, think of the middle of the map as Emerald City, and all the rotation that you do has to be around that point. So if you move 53 degrees this way, you're actually wait a minute, you move 53 degrees, but you don't change the length. That's multiplying by 1 over here. So if you multiply by the vector 1 at 53 degrees, what it does is it takes wherever you are and it moves you on a circle 53 degrees in a counterclockwise direction.
Got it.
And so that's multiplication. So now you know how to add and you know how to multiply again. And the only thing left is subtraction and division. Well, subtraction is just moving along the arrow in the opposite direction. So if I take this vector and I subtract the same vector and move in this direction, I end up where I started. So if I add this vector and subtract it, I'm going to end up with 0, just like I would if I had 3 minus 3 or 10 minus 10. I end up back where I started. If you want to subtract this vector from this vector, then you move this way in this direction. So just the point is, subtraction is just moving in the opposite direction from wherever the vector was pointing in the first place. And division is just moving the angle in the other direction. So if you want to divide, you go clockwise instead of counterclockwise.
But what is?
Now, addition, you use a lot to add up impedances like this. In division, you do to multiply, or multiplication, I'm sorry, you multiply a current times a voltage. It may not make a lot of sense to you, but if you want to get power, you multiply voltage times current. And in alternating circuits, everything is a vector, everything. Voltage, current, impedance, admittance, they're all vectors. They're all two-dimensional things. And you use addition, subtraction, multiplication, the same way you would use Ohm's law for simple circuits that you might have remembered from the technician stuff. That is, this is Ohm's law. To get a voltage, you multiply a current times what used to be resistance. Just don't use resistance, just use.
Goddamn thing.
Okay, so that's the exercise and why I had you do it.
Paul,
Yes,
let's play this out. So you have V1 is 6,
let
V2
me
is
go back
5.
to that. Let me go back to, okay, I'll go back to
Because I
it.
have no idea what you're talking about.
Okay,
So V1 is 6, V2 is 5. We add them together and get 11.
no, wait a minute, correction. V1 is not 5. V1
No,
is
it's 6.
5, wait a minute, V1 is 5 at 45 degrees. It's both of those two items that are necessary to talk about V1. V1 is not just a distance, it's a distance and a direction. So when I talk about V1, I don't mean one number, I mean two numbers.
So how do you calculate 6 at 135 degrees? What does that even mean? How do you do that mathematically?
Okay, wait a minute.
What number do you get at the end of this equation?
After you've done all three things?
I
After
guess,
you've
I
done
don't
all
know.
three,
The
you end up,
V1 plus V2,
that gets you to
times
Fall River
whatever.
over here.
what's the answer?
V1 plus V2 gets you to Fall River up here. Well, not
Yes,
Fall River.
but what is the answer to the equation?
What's the
It's a
answer?
mathematical equation,
Yeah,
correct?
yeah, okay. The answer is, wait a minute, I had it written down here. What did I do with it?
6 plus, okay, I don't know all that. I mean, I wouldn't even know how to calculate degrees in a,
Well,
in a mathematical equation.
Well, okay, I'm going to show you. If you see this V1 over here,
Yeah,
okay. Okay, V1 is 5. So instead of 5, let's use 50. See this 50?
okay,
And it's at minus 45 degrees. So forget that for a minute. That means when I move from here to here, I go 35.4 this way and 3.54 miles this way and 3.54 miles up.
okay.
You see that? In other words,
Yeah,
okay, so, all right, so that gets me to here. I go 3.5 this way and 3.5 up. Now, when I want to take V2, I'm going to move 4.2 this way and 4.2 up. And so the way you add these things in pieces is you can take 42 plus 35 and 42 plus 30. That should be the same number, though. That's not right. All right. What did I do wrong here? Let me, what am I doing wrong? I'm trying to create an explanation that may be wrong.
Oh,
Hold on.
I'll just do this.
If I add these two together, why don't I don't end up north. I end up just about 4 or 5 degrees off of north right over here.
Yeah,
So
yeah,
the answer is whatever this length is, which I think was 6.2 at minus 5 degrees. That's the answer to V1 plus V2. It's
is minus 5 degrees?
no, yeah, because I'm a little bit over from north.
Yeah, I can see that.
Okay. So the numerical answer to V1 plus V2 is, I had that written down. It's not like obvious number, but you could put your ruler on here and measure this distance.
Yeah,
And that's the length of this. So that's the length of that vector, and its angle is minus 5 degrees because it's 5 degrees this way.
got it.
Now, what I'm having trouble with is if this vector is 35 at 3.5 and 3.5, I should be able to add 3.54 and 4.42. And that should give me the number. So let me see what 42.42,
Okay.
35.4, 287, 7. So that's 7.82 miles. And then when I add them again, it seems like if I add those two numbers together, I just get straight up. Because 42 minus,
Right,
oh, wait a minute, no, 42 minus 35. Sorry, 40,
That's
yeah,
what I
right,
was thinking.
42 minus 35
Yes.
is 2071. So I'm 7.78 miles north and 1.7 miles west, which is, so I'm like I'm almost 7.8. This length here should be 7.8. This the length from here, and I'm 1.7 miles west on this side. That's what you're doing is you're adding these individual pieces. So if I add 42.2 to 35, that gives me 778. And if I subtract 35 from 42, I get 17. And that's the computation that gives me the position of this point at the top.
761.
And that should come out to about 8 miles at -5 degrees. I wasn't going to have you calculate that number, but if you want to know what it is, that's it.
No, I just didn't know what I didn't know what we were doing with it, that's all.
Now, if you want to move this around a circle, mechanically with a protractor, it's pretty easy to do. If you want to move this point to this point, mathematically, then you do have to use some trigonometry, which I'm trying to have you avoid.
Okay.
You can calculate this point directly from that number,
Okay.
okay? The point I'm trying to say is addition is to go one way and then follow this vector and then put that the new vector on the end, go in that direction. That's addition, and multiplication is rotation. That's the point I'm trying to make. Okay, sorry, that's a long explanation, but we're not getting to the material. But does that answer your question, Pat?
Yeah, sure.
Okay, if you want the exact calculation, I'd be happy to send it.
No, that I just didn't know what it was.
But that's the answer. Just add 44.242 and 3.54. That's one direction, and then 42 minus 35. That's the other one.
Okay.
Okay. All right. So what we're going to try to do in this week is we're going to try to cover these following sections of the exam: G1, C, D, and E, and G6, A, and B. So after we're done, you should go back to the Ham study guides and make sure you review the questions G1, C, D, and E, and G6, A, and B, and hopefully they will make sense to you. Okay? That's the general flow of this. I'm going to cover the material behind these sections, and then I'm expecting you to go back to Ham study and open up the pool of questions and go over this set of questions and see if you have any leftover ambiguity or whatever, and you want me to explain it next week, or you have a question, just send me the question and I'll try to explain it further. So we're going to talk about transmitter power regulations, data emissions, and 60-meter operation. These are very specific questions on the test. Okay. Unfortunately, like I've said before, the general test introduces all these words and doesn't give you any clue what they are. Okay. So the general is very difficult from an understanding point of view. Some of these words and things, you just got to almost memorize them, because they're not. I'm going to try to put some sense behind them, but frankly, there's way too many of them for you to completely understand everything that there are words for. All right, so this is what we're going to try to do now. So I'm going to keep moving. This is the same thing. I just repeated it. For Terry, the related extra section is E6, C, D, and E, and F on digital integrated circuits, inductor types, analog ICs, and electro-optics stuff. And there's slides in here that explain that, but I'm not going to spend a lot of time with most of you on that, because it's just, oh, and also in the extra section, there's a section E1F that you should review on miscellaneous rules. And that's a related area. Okay. This is all of the details of that extra section stuff, what's in those sections. That's just to remind me what's going on. Okay, some things that I think you should know about life. Okay, there are circuits called oscillators. If you had an ideal oscillator, it would produce something that vibrates at a very fixed rate, one frequency only. So an oscillator is something that produces a wave or a signal that vibrates at only one frequency, but that's what an oscillator is. If you had an ideal one, it would only produce one frequency. Now, real oscillators or ideal ones don't really exist. I mean, you can't make one that's perfect. So what happens is, if they don't produce one frequency, what do you think they do?
Create multiple frequencies. Hmm? Say again?
If an ideal oscillator only produces one frequency, what does an oscillator that's not ideal to produce?
Produces more than. one.
multiple.
Right.
Yeah.
And in order to create multiple frequencies, all you have to do is take a signal and move it around like a vector. So you vibrate it back and forth. You move the angle of the vector back and forth. And that changes the frequency. So frequencies have a character, oscillators have a characteristic thing called phase noise, which is the random frequency that they vibrate at. And the phase noise is what sort of creeps into a non-ideal oscillator. If you made an oscillator, it would never be one frequency. It might look like one frequency, but it's always got some kind of phase noise that moves the frequency around. So that's what an oscillator does, one frequency ideally. A modulator is another handy device in a radio. It actually creates frequencies. So if you feed an oscillator into a modulator, and then what will happen is you'll get more than one frequency at the output. And modulator is a word in the exam, and the highlighted words, by the way, are in the exam. So there's another word for modulator. It's called a mixer. So people talk about modulators, mixers, and multipliers. Now, what a modulator and a mixer really does is it just multiplies the values of two things that come in. So if I have a signal with a bunch of voltage, say, that's going up and down, and I have another one that's going up and down, what a mixer does is it simply does the arithmetic multiplication of those two things. That mathematics is nothing more than a multiplication. So modulators, mixers, and multipliers, all the same thing. Modulators are pretty complex thingies.
The same?
Okay, but if you don't have a modulator, you're never going to send any information on your radio. So when you multiply two signals together, and each one has one is, say, at frequency 1 and the other one is at frequency 2, when you mix them or multiply them together, you create the sum of the two frequencies and the difference of the two frequencies.
So you come out to zero.
So let's pick an example. I transmit at 3,500 kilohertz, 3.5 megahertz. And I mix it with 1 megahertz. What do I get out? I start at 3.5 and I mix it or multiply it or modulate it in a circuit. I multiply and I put in 1 megahertz as the other input. What do you think I get out?
3.5.
Nope.
4.5?
4.5.
Right? And 2.5.
Okay.
Okay?
So you add and
Yep.
subtract.
No,
And subtract.
that's a big change. A whole megahertz at 3.5 is a lot of frequency change. What really happens is your voice, for instance, is a typical thing you would mix with 3.5 megahertz. Your voice vibrates at about 1,000 times a second, or 1 kilohertz. Okay. So if I mix 3.5 megahertz with, let's say 3,500 kilohertz, 3.5 megahertz, 3,500 kilohertz with 1 kilohertz, what are the two frequencies I get out?
2.5 and 4.5.
What, anybody got it besides Pat, who's feverishly doing a great job here?
Yeah,
No, the 4.5 and the 2.5 is, again,
No, I mixed with
No?
one, not, before we mixed with 1 megahertz, which was 1,000.
oh,
Kilohertz.
okay.
Now we're only mixing with 1 kilohertz.
oh, one,
At
1
3.5.
kilohertz.
Okay,
Who wants to guess that? Mr.
That's-
Cahill there wants dying to.
so it's 3.6 and 3.4.
Huh?
Nope,
Nope, okay.
keep
Huh.
going. 3,501. I have 1 kilohertz and 3,500 kilohertz.
0.0035, which isn't the right answer. I went the wrong way, I think.
No, you didn't go the wrong way. You added 100 instead of 1 kilohertz. You added 100 kilohertz.
But you have to do it in megahertz, don't you?
You can do it in anything you want, but it's 3,500 plus or minus 1. Because 3,500 is in kilohertz. You have to, you can't add megahertz to kilohertz. No, you have
Correct.
you have to have them all in the same
I
unit.
thought
Yeah.
I did. But I didn't know whether I wanted kilohertz or megahertz.
Okay, so who's got the right answer now? Terry, you got the right answer?
No,
Okay. So again, 3,500 and I mix it with,
3501
and I mix it with 1. What do I get out?
Do you keep it in kilohertz?
Yeah,
Well, then it's
3,500 and I mix it with 1 kilohertz.
3,500 kilohertz.
What is it?
No, I don't know. I have no idea.
3500
Well, let me give you a hint. The first one is 3,501.
And the other one is,
34.99.
yes,
Right, there you go. So you see, by mixing sound with 35 megahertz, we only get a very small frequency change. You see that? We change it from 3,500 to 3,501, and we change 3,500 to 34.99. Any questions?
No.
So mixing creates, out of one frequency creates 2. And one is the sum of the 2 inputs and the other one is the difference of the 2 inputs. It's a pretty complex subject, actually. Don't think it's trivial, but it's really just addition of the frequencies instead of multiplication. The multiplication causes addition and subtraction. I could show you that mathematically, but I won't.
Don't, please don't.
Okay. All right. Okay. You know what I did do though? I did make an example of a mechanical thing that actually was a modulator. It was two rods, and I had a motor turning one of them, and the 2 rods were moving back and forth. And you can actually see that, but I'm not going to do that demonstration to take too much time. But in my files in the Dropbox is actually a spreadsheet simulation of a mechanical mixer where you take 2 sticks and you mix them together with a couple motors. The motors turning around are the 2 frequencies. So if you made this one go fast and this one, you would end up producing the difference in the sum of the 2 speeds of the motors. So, all right, so that's modulators. Okay. I talk about ideal resistors, ideal capacitors, inductors. There is a mathematical version of a resistor which says it's an ideal thing. That is, it only does what the mathematics wants it to do. When you actually physically hold one of these things in your hand, no component is ever ideal. There's always some little wacko thing that happens with a component to make it not be ideal. So But if you could make one, the mathematics says that these ideal parts, these things, will modify voltages and currents. And if they're ideal, they're called linear components. And linear components do not create new frequencies. Okay? So if you calculate the result of a linear component, you always have the same frequency as before, but you may have a little more or a little less of it. But you never create frequencies with ideal resistors, capacitors, inductors, and transformers. You only create frequencies by using what kind of circuit?
Modulator.
A modulator or a mixer or multiplier, okay? So there's the little things, there are ideal things and non-ideal things. And ideal components, the ones that we like to calculate with, resistors, capacitors, I'm going to show you some examples. They are linear components. A modulator is a what? Since it creates frequencies. If it's not linear, what is it?
Oscillating.
It's called nonlinear. It's not linear. Okay? So a modulator is a nonlinear circuit. A simple circuit with resistors, capacitors, inductors is a linear circuit. Okay, some more facts of life. A vector, we all know what that is now, right? A set of two numbers. A set of two numbers, a pair of numbers, they are ordered. We know that the first one is first, the second one is second. That's called a vector. The wind direction and speed is a vector. If I talk about the speed of the wind, is that a vector?
Yes.
No.
You need
No,
direction.
the
right?
speed and the
Correct.
direction. They're
So
two
I need
different.
to give you two numbers. I can tell you it's going northeast, and I can tell you it's going at 10 miles an hour. That's a vector. But if I give you only one of those two numbers,
One of the two numbers.
it's not a vector. Okay? After a while, vectors will start to sink in, and you will think of vectors just like you do the morning sun. Okay? You got to think vectors in this course. Okay? All right. I will mention vectors so often you'll be pulling your hair out. Okay. All right. When you have an alternating current in a circuit, which we talk about AC in our houses, AC in our outlets and stuff, all that means is that the current is changing. It's not constant. And if it's changing, we need vectors to describe that situation. So vectors are very important to radio circuits, and vectors are also important to any kind of analysis of an alternating current circuit or an alternating voltage circuit, which we don't call it that. Okay, you've heard of DC circuits in technician stuff. The direct current circuits, that a new term for everybody? No, shouldn't be.
No.
Okay. A direct current circuit is just an alternating current circuit where the frequency is 0. So I can lump a DC circuit into AC circuits by saying the frequency is simply 0. So there's really nothing special about DC other than the frequency is 0. So once you know how to do AC, you know how to do everything. DC is just a little piece of it. Okay. All right. Then there's another word called band. What is a band? A band is actually a group of frequencies. We're usually interested in a band for radio. We want to know the range of frequencies that we're allowed to use or are used by the signal that we put out. There's a difference. We're allowed to use frequencies in a certain band, but our signal, the one that we transmit, doesn't transmit all the frequencies in a band. It only transmits some of the band. The amount of that our radio sends is called the bandwidth of our signal. It's the range of frequencies that our signal puts out, not all the frequencies in the 40-meter band, for instance. So in our little, go back to our little example there where we had 3,500 kilohertz and we mixed it with 1 kilohertz, we produced two frequencies, 3501 and 3499. What's the difference between those two?
What were they? What were the numbers?
3500 was one mixer input, 30 and 1 kilohertz was the other mixer input. We mixed them or modulated them together, and we ended up with 3501 and 3499.
Mhm.
You recall from a minute ago. And
Right.
what's the difference between those two numbers?
3.
3?
2.
99,
2.
3,500.
1 minus 3499. It's 2.
You got 3499, you got
kilohertz.
3,500, you got 3,501.
Okay, but once we mix them together, both 3500 and 1 disappear. All we're left with is 3501 and 3499. So I got this black box, this magic box called a mixer. And in comes 3500 and in comes 1. What comes out is just 3501 and just 3499. The inputs go away and we created two new
Oh.
frequencies.
So
And so now we-
3,500's gone.
3500's gone. So is 1, by the way. So what we're transmitting is 3501 and 3499. So what's the difference between those two numbers?
Oh, 2. Yeah, that's 2.
Come on, guys, 3501 minus 3499.
That's 2.
2, yay! So our signal bandwidth is 2 now. That's what bandwidth means. When we're
Oh.
transmitting, if we were to transmit these this result of this mixer or modulator, we would transmit 3501 and 3499, and we would use up we would have sucked up all the frequencies in between because we're using those two and nobody can squeeze in between us. So our bandwidth in this case is 2. Now, which
Never-
band are we actually operating in?
Oh, well, wait a minute.
3500.
Oh, wait a minute.
Now you can go back to your band chart and find out what
That's my band chart.
yeah,
No,
me
I
go.
don't know where it is.
I can.
I can't read
Where
that.
I am
Well,
over
no,
here.
it's, I've got it in my cabinet, but I'm not gonna get it. This room's too
If you don't,
small.
if this is intriguing to you, I want to spend time on it because this is really fundamentally what's going on. All right, here we are, 3500. What
Yeah.
band are we in?
Oh,
80 meter.
We're in the 80 meter
Yep.
band, right? But we got a problem. Because one of our frequencies is 3499, right?
Mm-hmm.
Is that inside the 80 meter band?
Nope.
No. So we don't want to do that,
Ah,
okay? So
see that?
we should,
There
we
is
should-
no 340
yeah, so we should not modulate 3500.
that
because
close to the
mix-
edge.
If we mix something with 3500, we're going to spill over on the other side of 3500. And if we did it with 4000 or 4 megahertz, we would spill in the other direction.
Yep.
Mm-hmm.
We would be outside of the band. So
Yeah.
that would not be a legal signal to transmit. Interesting? No?
Yes,
really
no,
don't
yes,
care
I
about it.
want to learn about it. I want to, yeah.
Okay, so modulating signals creates frequencies. Those frequencies move from the original one we had, and they can go over the edge of the band above or below. And we have to be cognizant of that when we transmit signals, because otherwise we're going to move outside the band where we're not allowed to. So, so this will be a fundamental principle of all these things like single sideband, radio teletype, orthogonal frequency division, multiplexing, all these crazy modes, all have to worry about this problem. Okay, now you're all experts on bands, bandwidths, mixes, multipliers. and so forth. Really good general topic to worry about. Let me go back to, I gotta get back to where I was here. Okay, so you know what that is. All right, one more thing here. Let's see. Okay, so we talked about bands and falling outside of bands. If I make a signal and I change it instantaneously, what does that mean? Well, I got a current and I open a switch and it stops, right? If I had a switch in a circuit and I lift and I open the circuit, the current stops immediately, right? You agree with that? Yeah.
Like a
That's-
light switch.
Yeah, that's a really bad thing to do because it creates all kinds of frequencies. So when you form in your radio, when your radio formats a signal, it doesn't want to produce fast transitions on the antenna. It wants to make nice smooth things that change really smoothly. So corners and changes that make fast changes will produce all kinds of frequencies that could end up outside the band. So I've just given you this general concept that sharp corners are not good on radio signals. Okay.
Oh,
And if
yes.
you turn something, just turn something on and off, that causes a fast transition. So let me see, does that relate to, yeah, this is sort of the problem. Have you ever heard about a spot gap transmitter in the early days? Anybody heard of a spot gap transmitter? Well, that's probably
No.
not going to be a good representation of, but spot gap transmitters just made an arc. You know, when you get two high voltage signals and they start arcing across like lightning.
Yes,
Mhm.
Well, that's a very fast transition thing, and that creates frequencies all over the place. Even if the thing is tuned to produce more of one frequency, that arcing is creating frequencies all over the place. And you can tell that happens with lightning. If you're listening to the radio when there's lightning storm out, you're hearing crash, crash, crash. That's all the frequencies in the lightning that came out of this quick transition. So you can, that's an example of something that's, you know, you've heard radio noise from lightning. You call them static crashes. That creates frequencies. So linear circuits, do they create frequencies? Linear circuits, linear components, do they create frequencies?
Create frequencies. I don't know. Let's go. back.
no.
No.
we
If you have a
modulate.
linear thing, if you have a linear circuit and everything's ideal, you won't create any new frequencies with those circuits. You'll only modify whatever comes in to something else, but it won't change frequency. If you have a mixer, which is a nonlinear circuit, that will create new frequencies. And that's a general principle that we can use again and again here as we look at some very specific cases. These are very general rules. Okay. Okay. Now you know about oscillators, mixers, and the word linear components. I have not shown you linear components. I've just talked about them. Okay. What did I want to do here? Okay. Okay, I'm going to go to this. I'm going to try to go to this webpage here. Oops, I want that. Nope, I want to do that. Where's my browser here? What happened to my browser? I didn't want that either. Let me close that. I don't need that. I don't have a browser at all? Huh. Okay. Come on, beating control.
Uh-oh.
I didn't want to mute myself, sorry. All right, let's try to actually do something here.
We can't.
No, that's the wrong thing.
Back to mute. He won't let us.
All right, so let me go back. Why can't I just? Oh, come on. Why does it want to go to YouTube? I don't want to go to YouTube.
Why don't you do
What is going on here? Grab this. Copy it. Go here, paste it. It still wants to do YouTube. What the heck?
Wow.
Oh, there's good thing in that
They're
software.
big.
Is it-
I'm gonna have.
I don't know.
it-
No, I thought that they.
Paul,
Yes,
if you change the color to black, it won't do it. Blue means it's, blue means it's interactive and it's gonna take you to YouTube. If you change it to black like the text, it won't do it.
well, I just go to a new tab. It keeps going to YouTube. What the heck? I am totally confused here. Wait a minute. Why does it want to go to YouTube?
Because it's blue.
I think YouTube is playing games with me somehow.
Oh, I can't.
If you double click on that, it's gonna take you to YouTube.
No, it isn't, because it's not interactive. This is a photocopy. This is. They should
All right,
still.
let me do it a different way. Let me go to slideshow.
Yeah.
And go to current slide. And then I think maybe I can just. That's nothing. Okay, let me see if I can just go to this. Yeah, jeez. No. No, that's changing page. Why can I not? Why can I not go to this link?
Why can't you go where?
The link.
The link,
Oh, you should be able to.
I just want to go to this. Oh, it is. Oh, it is
Oh,
a
yeah.
YouTube, duh.
Why isn't it YouTube?
Oh, I thought he didn't want to go there.
My bad. My bad.
Hmm?
Give it a second. I didn't realize that my link was in fact a YouTube link. No. All right, well, guess what? I'll tell you something different. I did want to go to YouTube. This is last week's seminar on this link. Week 1 general extra.
Oh,
But when I post this week's recording, it'll be at that point, and you can look at last week's seminar. I lost the point of what I was trying to tell you, but I will send you this link as an email. I wanted to do that last week and I messed up. I didn't get a chance to do it. A little bit crazy week. All right, so that was about. So I apologize for that. That was my. I got tied up in a circle here.
I don't know.
This was not supposed. This was not supposed to be the link.
Ours doesn't. It's
Oh.
interesting.
All right,
know, it
well,
wasn't
let me get
when you
back on
first
track. I think this link got
This is not the
translated
same as that.
incorrectly.
exactly. I'm gonna write
This
it
was
down.
supposed to be another link and it got changed. I'll have to find it again.
I have it. When I printed it out, I have something different.
Yeah, I know.
Yeah.
I accidentally changed my slide to put this in there and that wasn't what I was supposed to have.
So
So
you,
I don't know what it was supposed to be, but
Well, can you tell us how to get to that YouTube page? Is it this?
Yeah,
is it this link?
yeah, yes, I can, but give me 1 second. I'll type it in.
The site gets interesting.
Where am I
Do
here?
you want us to go to the FCC site?
Yeah, that's all.
Oh,
It's-
well, that's what I have on my paper.
Yeah, I know. It's www.ecfr.gov
FCC.
/CGI -bin /text. Oh, we're not gonna do all of that. Let me just,
I just emailed it to you, Paul.
yeah, okay. It's this big, long, complicated thing, but
Yeah, yeah.
this is the basic page, okay? I showed you this last week. This is part 97. This is all the definitions
Oh, yeah.
of, this is all the definitions of all the words that the FCC uses. So that's, okay, I'm not at the final link, I'm just at the top of that link. And then in that link will be authorized bands, hopefully. Let me see if I can, oh, that was a mistake that I didn't catch. License procedures, station control, authorized transmissions. This is all the stuff that's indirectly in the exams. Where the heck is the authorized bands? Here's auxiliary stations, beacon stations, space stations. This is where all these things get defined that are in the exam. So if you don't know what a word is, you can read the definition of it at the FCC site. And that's what I was trying to show you. But I was also trying to go directly to the bands page. Here we go, authorized bands. My God, okay, technical standard subpart D 97.301. Oh, it's right there in the slide, 97.301. Dot. All right, so what ITU region are we in? Anybody remember?
Repeat?
What ITU region? See, here is the FCC. You can see this, right?
No,
You can't?
No,
You don't see the, what do
your
you see?
screen, we can't see your screen. I see the FCC regulations. That's the
slide.
slide.
Oh, okay, wait a minute, why are you not seeing? Oh, because I'm showing you the slides, I didn't want to do that. Okay, now do you see the
yes.
FCC site?
Yes,
Wow, sorry about that. All right, anyway, okay, so the FCC page shows you which bands are authorized by ITU region. Which ITU region are we in?
2.
Exactly. So this is the column that defines what bands we're authorized to use. Okay? And all right, so this one says, for a station having a control operator who has been granted a technician, general, advanced, or extra class. This is the following are available for use by anybody. If you have any license, you can use these bands, which is what you have privileges for now as technicians. These are all the 6 meter, 2 meter, 1.25, 70 centimeter bands. These are all the bands that you have the privileges to use if you have any license. However, if you have an extra class license, you are also authorized to use these additional bands in this list. So in this case, the FCC is telling you, here's what everybody can use. And then these are the very special frequencies you can use if you have an extra class license. They're not gonna care about that in the general test. They're gonna only care about the ones that you can do only as a general. And hopefully, there's also a thing called advanced class, which is which they don't make anymore. But some people have it. And then if you have a general class license, which is what you're gonna end up with, these are the new privileges that you will get. Okay? So I just wanted to show you where on the FCC site this was defined. Now,
And if you go to the
so
website.
if you, this is
Yes.
set up slightly differently than the band table. The band table shows you all the bands, and then with colors, it shows you which ones are general, which ones are extra, and so forth. This is the definition of the different classes of licenses. So I just want to show you this table because this is where the numbers come from. Okay? There used to be a thing called a novice class. And also a technician class. So you see that there are some special privileges even at 3.25 megahertz that you can do as technicians. You see that?
Yeah.
But you're only allowed to use A and I, which I believe are just Morse code. So you can't operate voice in these bands. You can only operate Morse related stuff. Okay. I don't recommend you use this table to figure out what's on the exam. I'm trying to show you where the numbers came from. The actual band plan should have all of those band plan tables should have all the information that you need for the exam. All right, so, all right. Sorry about that. We got really distracted there because I screwed up. All right, so this was section, this was supposed to be section 97.103, right?
103?
Yeah, and on section 97.113 provides 4 general standards for you to observe. On specifically specifically prohibited. The rule for you are not supposed to transmit for pay. You're not supposed to make money on amateur radio. Whoops. There's a question on pecuniary benefits for the station control operator. If you're teaching a class, you're allowed to be paid to teach the class, but you're not allowed to charge people to use the use of your privileges. Okay, and if I go back to the FCC page, I'm still at 303 here, right? So I need to go to what did I say, 113?
Yes.
Yes.
Sorry for the quick moving here, but oh, wait a minute, this is sorry, 303. So I wanted to go to 113.
Yes.
I'm too far down. Back up to, sorry, 203, 119, 113 should be here. All right, so these are prohibited. Okay, no amateur these are things you are not supposed to do. You're not supposed to communicate for hire or material compensation, direct or indirect, except as provided further. Communications in which a station licensee has pecuniary interest, that is, you make money, including communications on the behalf of an employer, is not authorized. You are not supposed to do that. You can, however, participate on behalf of an employer in an emergency preparedness or disaster drill, in which case most rules go away anyway. Okay. Tests, however, a test of like an emergency management exercise is not an emergency. So you're not allowed to break the rules just because you're on an exercise for an emergency. It has to be a real emergency. Okay. You're also restricted on the sale. You can notify other amateurs of the availability of a trade or apparatus. you can tell somebody I got something to sell. Okay, but you're not supposed to do it on a regular basis. So if you have a 3 o'clock in the afternoon equipment swap, that's not authorized. But you can tell some ham on the air that it's okay to, hey, I got a radio, you know, I'm planning to sell it. If you don't do it on a regular basis, that's authorized. Now, there's a special case where you can actually get paid if for an incident of a teaching position during periods of time when the amateur station is used by that teacher as part of a classroom. So if you're showing somebody how to run your radio as a teacher, it's okay to be paid as the teacher while you're teaching this. For that? In other words, you're not supposed to get money for letting people use your radio. But if you're showing them as a teacher how to use the radio, you can get paid as the teacher. That's a special case. These are little thingies in the exam that questions that are stuck in there. This is where they come from. Let's see, may accept compensation for telegraphy practice. So the teaching rule is, if you're teaching, the rules get pretty soft about not getting paid. But if you're just getting paid for doing it, no good. Music is not allowed except, let's see, music or phone emission. If you use any communications to facilitate a criminal act, if you try to obscure a message, you use obscene or indecent words, false deceptive messages, signals or identification, those are not allowed. So music's not allowed, and doing all these bad things is not allowed.
That's broadcasting.
And you will notice that in some cases, people violate these rules if you're listening to the shortwave bands. And these are specifically not allowed. And there are monitoring people that are amateur radio operators who volunteer their time to monitor the ham bands. And they often will send a notice to somebody if they regularly do this and tell them to knock it off. And if you don't knock it off, they'll report you to the FCC eventually. So you are being monitored for these things. If you hear them on the air, it's not really your job to go in and police it. But if you find an opportunity to mention it, that wouldn't be bad. I mean, I wouldn't break into a communication and say, hey, get off the air, you're being illegal. But a monitoring station would do this. They would take your call and they would send you a letter saying, or a notice that says, stop it. Okay, so that's how it's managed. Also, this is the place where the word purpose for obscuring a meaning. Now, this is still a soft legal point. The term encryption is not defined in any of these rules. There's only one place where encryption is specifically mentioned, and it has to do with controlling a satellite in space. So in theory, you're not supposed to obscure your message. Well, there's a lot of ways of obscuring messages without encrypting them. I mean, you could say, hey, I've got a sick patient 3 because I don't want to identify their name. Well, that's obscuring the name of the person, okay? So the FCC wouldn't have a big problem with that, but reality, it's obscuring the message. Now, if you're monitoring a race, a bicycle race or something, and that bicycle race has an injured person, that's an emergency situation. And so it would not be illegal in the sense to say, to de-identify patients by name, but by numbers or something. So those kind of rules are very soft. They're allowed, but in theory, you should never obscure a message on the air. You shouldn't come up with a code that says, when I say 3, it means, hey, some kind of obscene thing, for instance. I mean, that's not a lot. It's not allowed. So this is these are the details of these rules. And I point you to these FCC sites because this is where the rules come from. You can read all you want in the handbooks, but this is where the rules come from, okay? So anyway, I beat that to it. I beat that in. There's also this special case here, I think, of incidental music. You see that over there? It's a C, paragraph C. It says, including incidental music originating in United States government frequencies. So and it's associated earth stations. So if you retransmit something from the International Space Station and some astronaut happens to be playing music in the background, that's an incidental transmission of music. That's allowed under this rule. Now, this last one is an interesting one. If you're unless you're an auxiliary repeater or a space station, you should not automatically retransmit the radio signals of another station. So that's not talked about a whole lot, but if you're a repeater, that's allowed. But if you're a repeater, then you're under some other rules. Under normal conditions, you should not retransmit somebody else's thing. So if you run into a problem reading the questions and you don't know why they said that, this is the place to go to find out. And I believe I'm correct. If I go back to the general class questions, I lied. I thought that the regulation was actually in the, yeah, it is. If you look at a general class pool someplace, when you're dealing with regulations, they put a parenthetical in the general pool that says 97.221. That's the section of these rules that they're talking about in that question. So if you're not sure, you can always go to this reference and look up what the FCC actually said, and you can maybe gain some insight there instead of just knowing the answer to the question. I'll repeat it again. You can study for this exam. You can memorize all the questions. You can pass and get your license. There's no requirement that you really understand this material. I'm trying to give you some insight as to where this material comes from and where to go look in more detail after you pass your exam to know what's really going on. Okay, so I'm doing a little bit of both here. I'm teaching you to fish, and I'm catching a few fish for you along the way. Okay. I didn't stop at 7:30. Does anybody want to take a 5-minute break? You want to continue? Nobody needs a break? Okay, I'll continue. In the general class is an auxiliary station. This is where you can repeat. An amateur station as a repeater is remotely controlled over a radio link. There is still a control station though. Somebody is responsible for that repeater. You can't just stick a repeater and just to make it disappear. If you put your call, that repeater is required to produce its call sign. That's why when you're on 2 meters, every 10 minutes, the repeater goes, da 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 da, da 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 da. That's the repeater identification. Whoever is whoever is the control operator of record for that call sign is responsible for that station. So that's an auxiliary station, and just because you put one out does not mean if it's in your call, you're responsible for it. Okay. Now in repeaters, there's always the provision that a repeater might go bad, like something could go wrong, right? In which case you'd be transmitting illegally somehow, or somebody would use the repeater to in some improper way. That has happened, by the way. That's not that has happened. So the control operator of a repeater normally has a function that will shut the repeater off, and so that if there's any detected, if the repeater control operator detects that the repeater is doing something he can't control, he shuts it off. That's a requirement. You're supposed to be able to do that. So when you say, I want to put up a repeater, you have to say, hey, I've got this provision in place to shut it off if I detect it's not working correctly. And that could be both a bad transmitter or something wrong with it, or it could be somebody using it illegally, okay? So you can't stop them till they do it, but you can stop them after they do it. Any questions with that? Yeah, okay. Is this what I really wanted to show you? Yeah, I guess so. If you go to this website thing here, this is the one that I really wanted you to go to, I think. That will tell you about what signals you can transmit. You can't just use these frequencies arbitrarily. You'll have to use them within the authorized modes of what are called emissions. And we'll talk about all kinds of emissions in another seminar. However, there's a specific case here that might be worth talking about. The effective radiated power in the 60-meter band is described under FCC provision 97.313I. It says, first of all, what is ERP and EIRP? Okay. First of all, ERP is effective radiated power. It's how much power your transmitter is putting out. There's a very specific technical definition of it, but suppose I'm transmitting on a nice omnidirectional antenna. My power is getting distributed uniformly as it goes away from my antenna. That's called an isotropic antenna. If I had a little antenna in space and it was magically transmitting the same thing in all directions very uniformly, that would be called an isotropic antenna. Can you think of an example of a space, a thing in space that transmits light in all directions? You're on mute, guys. Anybody else want to suggest one?
The
What's a
sun,
thing in space, huh?
the sun,
The sun. So the sun is a good example of an isotropic antenna. It transmits just, I mean, it sort of sends special stuff, but in general, it's just producing light in all directions. So that's sort of a physical example of an isotropic antenna. It's actually a theoretical thing mathematically, but it just means that the light, all the radiation is just going out evenly in all directions. Now, if I make a dipole antenna, I'll call a half-wave dipole antenna, that does not radiate equally in all directions. So when I'm dealing with a very specific type of antenna, then I have to worry about what direction my power is going. And so when I'm talking about the effective radiated power, the reference point is really a half-wave dipole. So if somebody says EIRP, they mean the power of an equivalent, nice, perfectly isotropic device, whereas ERP is a more practical thing. It's what we really make. We don't make isotropic antennas. We have simple antennas like dipoles, and dipoles have some directionality to them. And so when we talk about ERP in the rules, we mean relative to a dipole antenna in a given direction. Okay, there's actually a computation in one of the not a computation, but a question that says, how do you convert? You multiply ERP by 1.64 to convert to an equivalent isotropically radiated power. So there's several A, B, C, D answers, and 1.64 is one of them. So I'm trying to give you a sense as to what that crazy, I mean, multiply EIP by 1.46 to convert to an equivalent isotropically radiated power. The goal of that question is not to let you repeat that sentence. It's just to tell you that there is a fixed constant that converts one to the other. Okay, there's another thing called peak envelope power. And this is called PEP. And it's the average power supplied to the antenna. The average power to the antenna transmission line during one cycle at the crest of the modulation envelope taken under normal operating circumstances. What the heck does that mean? Okay. So here's the section G1C, section questions 1 to 6, 14, and 15. They're all related to this power. A radio signal, if it was, now remember my original thing about 3500 before we put it into a mixer? Okay. This carrier signal picture is what that looks like. It's a wave that's going up and down. It's fixed. It has a fixed top and bottom, and it repeats. It's all one frequency. Okay. Our little 1 kilohertz thing, the one that we talked about, that changes and adds the frequencies back and forth to 3501 and 3499. It's a lot slower, right? It was like 1 kilohertz instead of 3500. If I mix those two things together in a mixer, what I get out is this thing at the bottom. All right. So if this is 0, then, oh, by the way, here's a picture of a mixer on the side here. Oh, you see this, right? So here's our information signal, and here's our oscillator sending out our carrier. And what comes out of the mixer is this waveform, which has little peaks and valleys in it. And I'm showing that at the bottom here. So when we're talking about peak envelope power, we're talking about not this, but the actual maximum point that this modulated signal does. So this signal is a little higher over here than it is here. So we have to use this maximum point to calculate this PEP. Now, the test isn't asking you to calculate PEP, but it wants you to have some sense of what it is. So, so you take the peak envelope signal, you find the maximum of this thing that's going up and down. That's the peak, right? You take 71% of it, which is 1 divided by the square root of 2, for those who like numbers. 71% is the magic number for what's called RMS power. We're going to revisit that later. But you take the voltage of that peak, you square it, and you divide it by 50 ohms. And that is what is called peak envelope power. There is no calculation like this in the test, but they do refer to peak envelope power as a thing. And there's the thing called peak envelope voltage instead of power, PEV, which is half of the peak to peak. So peak to peak is from this peak to that peak. See, from here to here. That's peak to peak signal. And then peak envelope voltage is from here to the maximum peak in one direction. So this graphic is trying to show you where peaks and peak to peaks are and how they relate to each other. All right, at the output of our little transmitter over here, you see I have 50 ohms over here and 50 ohms over here. What circuit is that from last week? Anybody remember? It starts with the word voltage. Voltage divider. You remember that term last week? I must have used it 10 times. No? anyway, this is a 50 ohm voltage divider, and they're equal, and it divides the voltage in two. So this is why I keep talking about voltage dividers, because they show up just like this in your radio signals. So this has got a lot of pictures and stuff in it, but you can go back and try to use this to figure out what these terms mean. This is the details of section G1C 16, 14, and 15, okay? Okay, back to voltage dividers, my favorite subject. If you don't remember the word voltage divider when you're done this thing, I'm gonna scream. Okay, now you don't need to know this diagram, but see the green line over here. All right, if I had remember we did 10 volts and we could divide the 10 volts into any number. So I could divide it by 1 and get 10, or I could divide it by infinity and get 0. But if I divided it in half, I'd get 5 volts. So the question is, if I divide it in 5, if I divide it in half, how much power does that, how much of that power is being absorbed by the load? Now, we want the load to absorb as much power as possible, because in an antenna, that's what radiates the signal. So the most power we can get into the load being the output thing instead of the source thing in this divider, which we just showed over here. This is the source impedance, and this is the load impedance. This is your antenna. This is all built into your radio. The amount of power that gets used up in this load is what we want to maximize. We want that to be as much power as possible, because we're going to have a louder signal on the air. So I did this calculation for you. You don't have to look, you don't have to do it. But if you note that when I divide by 2, I take 10 volts and I divide it by 2, the power curve is a peak. You see that? And so it's this magic point where if the source and the load are the same, the power is peaked. The most power gets delivered. If I divide it, if I leave it at 10 volts, the amount of power is not going to be the same. It's going to be 0, because in this case, all the power is not, no power is going to the load. And in this case, no power is going to the load. But if I do the calculations, which you don't have to do, the power peaks at halfway. That's the rule. Now, you've heard of the term standing wave ratio, SWR. We yak about it all the time on the air. When you're in the middle here in this voltage divider, the standing wave ratio is 1. That means that the load and the source are equal. Their ratio is 1. Okay. If I go anywhere else, if I change the source and I don't make them equal, I will get less power into the load. And so my standing wave ratio will go up. And this is just a drawing to show you that if I'm off a little bit, if the voltage was like 3.5, my standing wave ratio would be 2. And if it's off even more, the standing wave ratio keeps going up. So 4 and 10 and 20, and standing ratio in this case would be like 500. And if I go the other way, I get the same effect, because if I move away from this magic point, which I will ultimately call the Emerald City in the land of Zo, which is Oz spelled backwards. If I'm in the land of Zo, the Z0 or characteristic impedance, and I'm at the Emerald City, I'm right in the middle over here, and my SWR is 1. Everything's matched. The word matched gets placed, and the maximum power gets delivered to the load. If you do anything else, you don't get maximum power. That's the point. You don't need to calculate this. I just want to show you the whole picture. Okay. Here are some numbers for you to have some fun with. If you stick your finger in a wall socket, which I do not recommend, by the way, everybody calls that 120 volts, right? You know, you got a 120 volt plug on the wall. The 120 is actually called the RMS, or root mean square voltage. This thing that's going up and down is actually much bigger than 120 volts. The peak is actually 169 or 170 volts. So if the peak is 170 volts, how much is the peak to peak? Think about that. I've got this thing going up and down. It goes up 170. What's the difference between the two peaks? The answer's on the slide, by the way. Don't make it too high. I can't hear you, Pat. It's 340. It's twice as much.
Right.
Okay, so peak to peak is twice as much as peak. It's not so complicated, you know, with that half of its peak and the two peaks together, they're even, so it's twice as much. What's not obvious is if I put that much voltage into a 50 ohm resistor, I would generate 288 watts. Because I multiply the RMS voltage by squared divided by 50. That's the formula for power, and I get 288. So here's a bunch of examples. If I was in Europe and I had a 240 volt system, my peak would actually be 340 volts. My peak to peak would be this, and I'd be generating 1152 watts if I put that connection across a 50 ohm resistor. That's a lot of power, by the way. That's 1.1 kilowatt of power. The chances are the resistor would burn up and disappear. Okay, you can put 1,000 watts out into an antenna, and note that if you were to put 1,000 volts onto if you were to try to transmit 1 kilowatt, which you're allowed to do, those voltages would be really big. You would have 340 volts on your coax line, and that would kill you. So don't do that. So when you're transmitting 1,000 watts or 1,150 watts, those peak voltages on those circuits are like 340 volts, not safe. So I threw in a bunch of other numbers if you want to play games. I suggest that you try this homework exercise next week and try to understand this by doing these things. These are not specifically things that you have to do on a test, but they're just there for your to help you understand how to use these formulas and what they mean. So here's a homework exercise for you. I will, by the way, post these things as a PDF on the site. They're already there, actually, already. Like under the week 2 PDF, you can get this stuff and look at the slides. All right. Let's see. Okay, I gotta keep moving it. G1C on power. G1C talks about power, a thing called RTTY, and 60 meters. So we talked about PEP, that's peak envelope power. There's another question about 71% of peak envelope voltage. Well, I don't remember the question though. I think these are just examples I made. Power is voltage times current. But if current is voltage times resistance, you end up with voltage times voltage divided by resistance. And that's where the formula V squared divided by R comes from. I hate algebra like this, but if you want to understand it, you got to multiply voltage by itself and divide by the resistance. By the way, this 71% thing shows up all over the place. It's a magic constant. 71% is just 45 degrees. It's just a vector at 45 degrees. So if I have something that's length 1 and it's at 45 degrees, the vertical part of it is 71%. It's 71% this way, 71% that way. So 71% is not something out of the blue. It's just the length of a vector on the east or west, north or east direction, if the vector is at 45 degrees. I'm just trying to relate the 71% to you. You can play the game and divide by, you multiply the square root of 2 by itself and you end up with 2. 71% is not exactly right either. It's almost 71%, but for all practical purposes, 71% is a good number to use. Okay. One of the other questions, oh, wait a minute, this is, sorry, this is, all right. This is not for you guys, it's for Terry. There's a question, E1C9 on angle modulation. So this is some special extra stuff. And there's a nice reference there that talks all about frequency modulation, if you want to look at where this comes from. So I'm giving you a frequency
Okay.
modulation reference if you want to look you want to get a little bit deeper understanding of this.
Okay.
This one question though on FM modulation index, I think it's very obscure. You might want to just memorize this one.
Okay.
But it's there if you want to know.
Okay.
All right. Here's a few pictures here. We talked about this effective radiated power. A dipole, this is a dipole. It's a piece of wire that goes this way and that way, and it's fed in the middle from your radio. I don't think G5RV is in the exam, but if I recall, but G5RV is a very popular antenna. A lot of people have them. Mark Flaherty has one, for instance. But it's built this way. It's just a piece of wire, 1/4 wavelength this way and 1/4 wavelength that way. But wavelength is 300 divided by the frequency. So 300 divided by 150 megahertz is 2 meters, right? That's 2 meters is the whole wavelength. Half of 2 meters is 1 meter. 1 meter is about 6 feet. So a 2 meter dipole is 2 halves. So it's, instead of 6 feet, it's 3 feet and 3 feet. So the whole thing is about 6 feet long. So you start off, I got a frequency, I want to operate on 2 meters, 300 divided by the frequency, 300 divided by 150, 2 meters. 2 meters is about 6 feet. Half of that is half the wavelength, 1 meter. Half of that is a 1/4 wavelength, 3 feet. So it's about a yard and a yard, 2 yardsticks of wire. You got a 2 meter dipole. Okay. So that's what, and these dipoles radiate in this pattern over here on the side, and they pretty much, this is horizontal and this is vertical. There is supposedly a hole in the middle where they don't transmit off the ends of the dipole. So there's no radiation in theory off the ends of the dipole. Doesn't really happen. That point where they would theoretically not transmit, there's all kinds of effects like leaves in the trees and ground and wetness in the air and all kinds of stuff that will not make that actually do that unless you're in very constrained conditions. So a real dipole just basically transmits more or less in all directions, but it has a little bit of gain in one direction. And that gain is 2.15 dB. So there's a conversion factor from an isotropic, the sun, to a dipole, which has a little bit of specialization that's not completely round. It's got a little bit of pointiness to it. And that difference computes very complicated way computes to 2.15 decibels of gain in a dipole antenna. Now, some antennas have a lot more gain, and this is one of them, this Yagi antenna. This is one we make out of measuring tape. So you go down to Harbor Freight, and you buy some measuring tape, and you adjust it for 2 meters. How long should each piece be? For 2 meters.
1 meter apiece?
Yeah, the whole thing should be 6 feet. I'm sorry, 2 meters, 2 meters, I'm sorry, 2 meters, did I do that right? 2 meters is, yeah, 2 meters is 12 feet. Half of that is the length of the whole length of the dipole, 3 feet.
Wait a
And,
minute.
and it's a yardstick away the other way, so it's 36 inches.
2 meters is
So,
12 feet.
so anyway, if I build this structure here of stuff, somebody's talking to me in the background. Who is that?
Bob's
Well, I
TV,
think it's just Bob's thing again.
mute him.
Okay, all right, so actually I have one of these in the garage if you want to see it, but that's called a Yagi antenna. And you do that so that in one direction, you transmit a lot of stuff, and in the back, you don't transmit as much. So that makes the antenna point in a given direction. Now, there is no such thing as gain in an antenna. Okay, antennas don't transmit more in one direction than the other, relative to what they would do if they were just transmitting in all directions. All that you do is you take whatever energy you're going to be transmitting, think of it as a balloon, okay? And if you want to make it point in one direction, you squish the balloon, and the balloon will point in one direction, and other things will happen to the balloon, but the whole sum of the whole thing is no different than if you let the balloon go and it's the whole balloon. So antennas are basically like a shape that you kind of smush on and make it do what you want. But you don't get more out than you would have if you let the balloon be uniform. However, if you want to think of it relative to something, there is more going out in one direction than the other. So that's what the gain of the antenna is referring to. It says, I'm going to put out twice as much in this direction as that direction, right? But that's because I organized the balloon. So these things like squish, you see these little side lobes here? It's like, it works just like a balloon. That's the best example I have. You squeeze on the antenna and you can bet that the energy is going to squirt out someplace else. It just doesn't magically produce more energy. It just directs the energy in a specific way. And so by putting more energy this way, you've taken that energy from someplace else, like in behind. So that's why antennas have these various shapes. And these shapes are pretty complicated to calculate, but they're well defined and they've been calculated for a lot of different cases. So you can look these things up, but that's the point I'm trying to make. So usually there's some reference antenna, and usually the reference antenna is a dipole, because that's an easy thing to make and it's an easy thing to measure. So that's what most of the FCC people reference. They reference a dipole. You cannot make an isotropic antenna anyway, so and you're not going to make a sun for your backyard. So don't make an isotropic antenna, make a dipole. Okay. Okay. Where am I at? I lost my paper. All right. There's a section of the exam on volunteer examiners. You've all experienced volunteer examiners because they come and administer the test. you have to have a license to be a volunteer examiner. And question D1 relates to you have to have a license. If your license is revoked, you can no longer be a volunteer examiner. There's a whole bunch of reasons you don't want to ever get your license revoked. So don't get your, so bottom line in that question is don't get your license revoked. For these questions, if you're a general, you can administer technician licenses. If you're an extra, you can do both of them. That's not too complicated a rule. General can do tech, extra can do both. There's 3 questions on that. There are also 3 questions as a certificate of successful completion. If you have a certificate of successful completion on a general exam, when you get your general, you have the privilege of operating, but you have to add the /AG at the end of your call that says, well, I passed the test, but I haven't got my official notice yet. So you'll be able to transmit legally as long as you have a certificate of successful completion. And that's the point behind those 3 questions in the exam. D07, I don't even remember what that is. G1, D07. Oh, who accredits volunteer examiners is the question. And this is the one case where the FCC doesn't do it. The volunteer examiners, there are only 7 organizations that do this. And the volunteer examiner group is are the people that accredit a volunteer examiner. They give the test to become a volunteer examiner. This is the one case where the organization that does the authorization is not the FCC. Okay, and it's a question 8 and 10. These are all related to certificate of completion. One of them is how good is it? It's good for 1 year. And D11 is, I must have had something trickier. This is what's required to obtain a general class license after a previously held license expires and the grace period has expired. And let me see, that's the 11. If you look at 95.505, I'm not going to have time to really do that, but the answer is, the answer is the applicant must pass the current element 2 exam. And if you look at
Technician.
if you look at element 2 is not, it's not like 1, it's element, if you look at 97.505, element 2 is not in column 3, and I'd have to go there to show you, but I'm gonna just go past that because I think you're gonna memorize that one. Also, questions D8 and 10, a volunteer examiner has to have an FCC license because by the rule up here, it says you have to be a general class license to give tech exams. If you're an extra, you can do both. But you also have to be 18 years old. So youth that get their license are not allowed to be volunteer examiners. And those are the questions, okay? There's no real theory there, it's just the rules. All right, radio teletype. Everybody's probably heard of teletypes. They're really old things. But as amateurs, you're still allowed to use them. And so the radio teletype machine is capable of reading a paper tape. I'm going to show you. Here's a piece of paper, perforated paper tape. See it down here? I don't know if you've ever seen this stuff, but you see this 5 dots on the tape. If you look at all the combinations vertically, There's no more than 5. There's 2 at the top and 3 at the bottom. That's a 5-bit code. So if I want the letter A, I have hole, and 3 no holes. The letter B, you don't have to know these letters, but I'm just trying to show you how the code works. The letter B is 1 hole, no hole, and 2 holes. Follow that? So you can go back to the slide and you can see what the rule is, what the letters are. And this is a teletype keyboard. And there's a shift button that goes from lowercase to uppercase. Notice that an uppercase A is not a little a, it's an arrow. Okay, and the numbers are actually uppercase letters, like O is a 9. And you don't have to know this code. I'm sorry if I'm making you think that, but this 5-bit code is called the Baudot code, B-A-U-D-O-T. I'll go back here a second. A 5-bit Baudot code is being used to make one character. So if I want to send the letter A, I have to send 5 individual things that will be in the pattern that I just showed you. And the name of this code is called the Baudot code, B-A-U-D-O-T. So I think the word Baudot code appears in a license. Now, basically, if I send you this one string of holes and no holes, I'm sending you 5 things. But there's a speed at which I send it to you. It's just like Morse code, did it, da, 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 did it, da, da, da. If I do it really fast, I'm increasing the data rate that I'm sending to you, right? The higher the data rate, the speed at which I send these pulses of holes or not holes is called baud rate. So it's the beginning of the word Baudot. See it? So Baudot is the code, baud rate is the speed at which I send the individual things. Now, remember when we went from 3500 to 3501 and 3499? The faster I send the dots, or the faster I send the code, the further away those modulating signals get from the middle. So if I send them really fast, I'm going to transmit on either side of my carrier. If I transmit very slowly, I'm just going to transmit very close to the carrier. So if I transmit very fast, my signal takes more frequencies. And if I was near the end of the band, I could fall off the end, right? Remember we did that? 35, 44, 99 was past the end of the band because I expanded my carrier around those numbers. So the FCC has a special set of rules to limit how fast you can transmit these transitions from holes to no holes. And they're all in the test. So if you're below 28 megahertz, like you're in 10 meters, 10, 15, 60, 40, 80 meters, you can only transmit 300 of those per second. If you're in the 10-meter band, that is, you're not below 28, you're in the 10-meter band, you're allowed to transmit 1,200 of them per second. If you're above, let's see, so it's 10-meter band. Above 2 meters, you're allowed to make it even faster. You can go to 19,600 holes, equivalent holes per second. And you can operate as high as 56,000 baud in these higher frequency bands, like 1.25 meters. And if you're above 1.25, which means that you've got bigger bandwidths than 1.25. So remember, when the bandwidth gets when the wavelength gets long, the frequency gets short. So there's this step, you can transmit in the HF bands, you can transmit 300 baud at 10 meters, you can do 1200. Above 2 meters, like 2 meters and 440 and those things, you can transmit up to 19.6. But if you get up to 240 megahertz, which is 1.25 meters, you can transmit really fast, 56,000. So at the higher frequencies, you're allowed to transmit faster and faster radio signals. And that's a general rule, okay? But these are the very specific places that you'll have to remember, because I don't know they won't ask you all these questions. They're only going to ask you one of these, but you got to know which one's which. So there's some questions associated with that. Let's see. No, that was kind of went back and forth. All right. Kind of past the time, but I want to show you. I came up with this crazy series parallel thing. I call it sunrise instead of sunrise. And what it means is if you have resistors or inductors and they're in series, you sum their values together. So if you can remember what sunrise means, you always sum in series. You sum resistors values and inductor values in series. If they're not in series, then you have to use the opposite rule. So it's kind of like it's like if you have there's two inversions. If you have resistors and inductors, therefore the RI and rise. This is sort of a device to try to remember. Resistors and inductors, you sum them. Capacitors are the opposite case. So here are the four cases. Resistors and inductors in series is sunrise. If it's a capacitor, then you use a different rule. I'll explain. If you have resistors and inductors in parallel, you use that rule. And if you have capacitors in parallel, you add them together. So if you can get this one right, you should be able to do the other three. But what I find most people forget is they don't remember which one is which first. So the way I do it is, if you can remember summarize, when you get to the exam, I would write down this table quickly using the rule, and then you have a little cheat sheet to go back to. You can't take the table into the exam, but before you take the exam, you could write this down so that if you need to refer to it, you can refer to it quickly during the exam. I recommend that in general. You can't memorize too many things to write down, but I would write down like Ohm's law. I would write down 300 divided by the frequency, and I would write the summarize thing so that I could refer to it when I get to that question in the test. I don't have to go back and think of the rule. I've got it written down for me. So that's another little trick to taking the test, is to take the things you have the most trouble with and remember those and write them down right away before you take the test. Okay, so if I had two capacitors and I put them in series, the way you calculate that is you multiply the two values together and you divide by the sum. So you either add them together alone, you just add them together. So if I had one resistor of 10 ohms and one resistor of 20 ohms, I add them together and that makes an equivalent of 10 plus 20 or 30. But if I had a capacitor, which is this looking thing, and I connect them in series, that is, I connect them like this. I don't add the values. What I do is I take the multiplication of the values and I divide it by the sum. In all cases, you're at least calculating the sum, right? Because if you're going to just do the sum, you do the sum. If you want to do the product over the sum, you have to calculate the sum as well. So always add them up. Okay. So if I had a 20 microfarad and a 30 microfarad capacitor, I multiply them together. 20 times 30 gives me 600. I add them together, which is 20 plus 30, that's 50. and I divide the product 600 by the sum 50, and two capacitors in series have the equivalent of 12. So there's only two rules you're dealing with. Add them up or multiply them and divide them by the addition. That's the only rules. But you have to know whether they're resistors or capacitors, and you have to know if they're in series or in parallel. This slide will give you all those cases. There's not 1,000 other cases. That's it. So this is a little tricky. I like to start with summarize and then just write down the rest of the rules, because capacitors are different and series and parallel are different. That's the 4 sets. Practice making this table, and you can draw it quickly on the exam on a piece of scratch paper, and then you can refer to it when you have a question. So there are only two rules: atom or product over sum. There is this product over sum thing, I'm going to mention the word, is an old formula called the reciprocal of the answer is the sum of the two reciprocals. If you like that language, go ahead. God bless you. But I don't like to use that technique. I like to multiply them together and divide by the sum. And that's a much simpler rule, even though it's not zero complicated. All right, so that's that thing. What was this one about? This is another example of another voltage divider. I'm trying to remember why I had this in here. This is just to show you how to use the circuits thing. That's not in the test. Oh, sorry. This does have, see these two resistors over here, they're connected. Are those in series? See these two, this is a resistor and that's a resistor, and they're connected this way. Is that in series or in parallel? Okay. I can't hear you guys.
Series.
It's in series. You had your mic off. That's a series connection. Okay, this resistor and this resistor are in parallel. See, this one, the top and bottom of these things are connected to the top and bottom of this. All this stuff on the side has nothing to do with the parallel thing. This is a resistor in parallel with another one, and some of the water or the current flows this way and some of it goes this way. So it sort of splits the current as it goes down the two. If they're in series, the same current goes through both of them. They're in parallel, the current comes in, gets split up and comes back together at the bottom. That's what parallel means. This is an example. If you were playing with Tinkercad circuits, you could try this. What was this one? I put a switch in so you could turn this thing on and off. I don't think there's anything really new here, but it's an example. Am I in the same? Hold on a second. Okay, I want to end with this. I'll go back to the lightning thing in a second if we got a minute. This is the picture that's on the general class exam. There's only one picture, G7-1. And in that picture are all these little components. These little squiggly things are resistors. These things are called capacitors. Here's what I did. You see they're all numbered 11, 4, 8, 5, whatever, 6. The exam has in G7, of all the things that are on this diagram, the only ones that are in the exam are 1, 2, 5, 6, and 7. So make sure you know what 1, 2, 5, 6, and 7 is, because they're not going to ask you about 4, and they're not going to ask you about 8 and 9. I went through the test and I figured out that only 1, 2, 5, 6, and 7 are referred to. So here's 1. It's a FET or a field effect transistor. Notice the line is straight in the middle. That the line in the middle is straight, but that the wiring goes directly and perpendicular to this vertical line. That makes a field effect transistor. If you look at 2, that's an NPN transistor. You see the lines are angled as they leave the middle. If it's a NPN transistor, which this is, don't worry about the NPN. This is a transistor type. This is a field effect transistor if the lines are perpendicular. 5 is a Zener diode. It's got this little quirky little top to it. So it's got the triangle. These are all diodes. This is a diode. This is a diode. But a Zener diode has this little shape on the top. Okay, so that's in the test. The interesting thing is they won't ask you for 3 because that's not highlighted here, but they will ask you which one is a Zener diode. That's 5. A transformer is shown as this little coil thing, which is actually what it is. I mean, the wire is actually wrapped around one side, and then there's another wire that's wrapped around the other side, and that makes a transformer. You can take a piece of metal, you can wrap a wire on this side of the metal and wrap a wire on the other side. That makes a transformer too. They use the term solid core. Now, the reason you can tell it's a solid core is it's got these bars in between in the symbol. This is just a symbol, but if it's a solid core transformer, it has those lines in there. They're not going to fool you with that. They're really just going to ask you which one is a solid core transformer. And there's only one transformer in the whole picture. It's not that hard a question, but they will ask you about solid core. They will throw the word solid core in there to try to trick you. This bar in the middle is what makes it a solid core. So that might help you. And then the last thing is a tapped inductor. Which is this number 7 down here. So this is an inductor. There's only one coil that makes it an inductor, but there's a wire connected to the middle of it, tapping into it. That's why they call it a tapped inductor. Okay. And all the other stuff, I gave you the names, but they're not in the exam. So 1, 2, 5, 6, and 7 are the symbols you kind of have to memorize for the general. My question on this one is I keep talking to you about voltage dividers. What I'd like you to do is when you look at this diagram, and this isn't in the test, but try to find how many voltage dividers you can find in this diagram. And have a ball. So I'm trying to help you find voltage dividers. The fact that they're connected to other things is not, if you take any 2 components and they're looked up and they're wired, this guy and that guy, that's a voltage divider. And you can use that voltage divider theory I'm trying to show you to analyze this whole circuit at some point.
7, did you get 7?
Any question? Yeah, go ahead, Pat. This question?
Point to a voltage divider.
6.
Okay. See this 10? See this
Yeah.
resistor? This little thing over here?
Okay, number
One
10, yeah.
component, that's another one. That's a voltage divider. See this guy over here? There's another capacitor and a resistor. That's a voltage divider. Whoops, sorry about that.
So I got 1, 2, 3.
See this
4,
resistor
5,
here? And
8,
this
9,
resistor?
11,
They're
12,
connected together
13,
like that?
15.
That's a voltage divider. This resistor and that resistor, it's just that instead of flipping it sideways, it's vertical. So these 2 together form a voltage divider.
Are there 15?
15, how many are there? Is that your question?
Yeah,
I think there's 15, but I don't remember. I have to think about it. I just wanted to give you the problem to think about. The reason I'm saying this is, I don't care if you know how many there are in this drawing. What I care about is that you kind of recognize them right away. Anytime you see two components together, the analysis of a voltage divider can be used to solve that problem without having to look at this whole thing and say, oh, what does that do? You break it up into little pieces and you analyze each piece if you had to. So the test really has to do only with recognizing these components, okay? There's nothing about specifically voltage dividers. If you're an extra, if you're working on your extra like Terry, this circuit is actually a Morse code transmitter, and it consists of this item 4, which is actually a varactor tunable. This is a varactor or a variable capacitor, and it's in this whole circuit is a tunable Hartley oscillator over here, followed by what's called a Class A amplifier over here. So this is extra class stuff, but this as an actual thing. It's not just a bunch of wires thrown together on a diagram. Okay. The one thing I didn't talk about, I'm going to go back 2 slides. What is a source? A source is where you get power for a radio or a battery. It's a plug in your wall. A source creates electric current. And there are DC sources, which you have all around your house, called batteries. A battery is a DC source. It's where you get current that just flows constantly. A power supply is a box with a knob on it and a switch. That's also a DC source, like a wall wart, something you plug in the wall to power a little thing. That's usually a DC power source. There are also things that create alternating current. And some examples of those are radio transmitters that produce wiggly waves to produce radio waves. A microphone produces your sound and wiggles. That's an AC power source. You can get a magic box called a function generator, whose very job is to create this. That's a design. And then there are test equipments that called SWR analyzers, vector network analyzers, noise generators. These are all things that generate alternating current. And another alternating current source is sparks and lightning. And I give you a reference here, I know some about it, but I talked about lightning here. Lightning is actually a radio wave. Lightning is the discharge of electricity, but because it's vibrating, it's not just a straight current. You know, it's moving around. As soon as the electricity moves, changes current, it's oscillating, and that creates radio waves. So lightning, here's some information about what radio waves lightning creates. And I don't think this is specifically about a question. So this is information for you. At that point, no, I did skip something. 2 questions. G6A talks about resistors. This is a wire round resistor. It's just wire round around. Looks like an inductor, but it's actually bad for radio frequencies. These are the other questions. So you can look this over if you have I think you're going to almost have to memorize these, but here's some details on my thoughts about wire round. They're bad for radio frequencies because they act like inductors. Inductors can have a ferrite core, that's discussed. But after a while, you got this coil, which is a bunch of wires, but it's actually a bunch of conductors that are near each other, because as the thing goes around, there's actually, it actually looks like two plates of with something in between, with no conducting in between. That would look like a capacitor. So as the frequency goes way up on a coil, the capacitor part of this mechanical, this is a non-ideal thing. Remember, we talked about ideal inductors. A non-ideal effect is that this capacitance, and in one of the questions says a capacitor acts like a self-resonant frequency, and it's a non-ideal behavior. All right, so that's 6A. 6A, a lead acid battery. I think you might know these things. Oh, a silicon diode question. What is the threshold voltage? A silicon diode has a 0.7 volt threshold. You won't remember, you may not remember 0.7, but remember 7 and silicon both start with S. So in the test, the only answer is 0.7 and some other stuff. So if you can equate silicon and S, you'll be able to get that one right. And another number they throw at you is if you got a 12 volt battery and it's only 10.5 volts, it's not going to work well. So that's another thing. And I'm going to end it there.
I can know that because everything's right there. It's not.
Next week, I'll show you about impedance vectors. By the way, this drawing that I showed you last week shows you all of the names of the impedance vectors. And so keep this thing handy, and you can see all the words: impedance, reactance, susceptance, admittance, resistance, conductance. All the words are on here, and they all relate to these simple vectors that we've talked about. And so that's kind of a reference drawing. If you could draw this drawing for yourself and write all those words down, you'd be an expert at this. That would be one way to do it, is make the list of words and then try to draw this picture and put the words where they belong. Okay? All right, it's 9 o'clock, so I think we better quit.
Well, that's great.
Any questions before we leave tonight?
Yes, Paul.
Yeah,
I noticed on one of the slides, one of the more.
wait a minute, you're doing it again. Talk into the microphone.
I'm not sure where the microphone
You
is.
keep moving off to the side and I lose you in the sound.
On one of the slides that we looked at tonight, in the last 10 minutes or so, there was a number, and then it had lowercase u, capital F. What did that stand for? Do you remember?
Let me back up. Maybe tell me to stop when you think you saw the slide.
There it was. Yeah.
UF, okay. Sorry about that. That is the abbreviation for microfarad.
Oh.
Okay, so let me go back here to slide 10. And see over here on this Greek thing, it says micro.
Yes.
See the U?
Yeah.
Yes.
When you put the U in front, it means micro something. So micro henries or microfarads, you put UH or
Okay.
UC if you mean micro farads. It's the abbreviation for moving the decimal place 6 to the left. Now, I use a U. It's actually a Greek letter. Sometimes they use a Greek letter called mu, which looks like a U, but it's got a little tail. It's like a backwards flipped over Y. But
We use that. We use that in healthcare. That's what I said, oh, I wonder if they change that little thing to a
No,
U.
it mu, the U is really the Greek letter mu, and mu is used all over the place. Yeah, it's in healthcare too, sure.
Yeah.
Yep.
Go.
M is milli, U is micro, N is nano, and P is pico. So PF means picofarads. And
Got it.
capital T hertz is terahertz. Gigahertz,
Okay.
megahertz, and kilovolts. See, I used the lowercase k over here. Because you don't use the capital K for
Right,
kilo.
right.
Yeah, which I think is stupid, but hey, what do I know?
All right, time to go.
Okay, have a good evening, everybody, and take a look at the
Thanks,
questions.
Paul.
Thank you,
And you'll
Paul.
find everything I said in the questions in those sections, okay? Good night,
Okay, good night.
Thank you,
for your time.
Paul.
no problem.
I'm gonna tackle my
Oop, I gotta shut off the recording too.